So in the last class, I just gave a very high level overview of what kind of problems we want to solve in machine learning. And I mean, there are these engineering problems that we would like to solve. And the first step is always to pose them as one of these standard learning tasks, either classification or regression or ranking, clustering, and so on. Right. So once we've done that, we can try to analyze how do you perform classification or regression. Now we have abstract problems that we can work with, and the main goal of this particular course will be to really mathematically analyze some of these learning tasks. In particular, statistical learning theory is what it tries to do is pose each of these as rigorous mathematical problems and try to derive bounds on what is possible and what is not possible in different scenarios. And in this course, we'll exclusively focus on supervised learning, which means that you're given a data set. So there's an underlying problem that you want to solve that is of prediction. And the assumption is that you have a bunch of training data which you can use to design an algorithm which can then be used in practice. And the goal of this course will be to see how do you design an algorithm to do this. And once we've designed the algorithm, how do we measure the performance of such an algorithm? Right. And so in supervised learning, the fundamental assumption is that the data that you have, the training data that is provided to you, is labeled. So you're given you're given a bunch of examples or instances and the corresponding labels. And the goal is to design an algorithm that will predict the label for an unseen instance. Okay, so we started out with defining certain basic terms: the domain set, that is where the examples come from; the label set, that is a set of labels that it corresponds to. So the domain set could potentially be say the set of all possible emails of a certain character length, or the set of all songs of a certain duration, or all possible images with certain dimensions. And the labels could correspondingly be, for the email example, it could be whether it is spam or not. Those are two different labels. Songs, it could be maybe you want to classify it into different genres. So the set of all possible genres is the label set. For images, maybe you want to say whether there is a particular kind of an object, maybe a car or a cat or a dog in it or not, and whether it is present or not, that is the set of labels. Right. So in order to be able to mathematically say something about these problems, we need to make certain assumptions on the ground truth. That is, how is the data actually generated? So we'll use the simplest yet most general framework for this. That is, the ground truth is, you can view the ground truth as some sort of a black box. There is something that is true. So given an input, this black box outputs what the label is. And we can make one of two assumptions: either that this black box is actually a function, so the label is a deterministic function of the instance, in which case we call this true function, or the ground truth function, as a concept, and the set of all ground truth functions is called a concept class. Or we can make a more general assumption, that is, the example or the instance itself is insufficient to exactly determine the label, and there is still some more information that is missing, or some more residual uncertainty that is left out. So the label is in fact a random quantity that is conditionally dependent on the example. Right. So the instance and the label are jointly distributed according to some unknown distribution Pxy. Okay. And the assumption that we will make is that the training data is nothing but a bunch of independent and identically distributed samples. So it's independent and identically distributed pairs of instances and their corresponding labels, and they're all drawn from the ground truth distribution. All right. Okay. So now towards the end of the class, I was getting to so what is the learner supposed to output? You're given this training data, what is the end goal? So the end goal is to output some function. We'll look at deterministic functions. So the goal is the goal of the learner is to output some function based on the training set, which for every instance will predict the corresponding label. All right. And the goal is, intuitively, the goal is to ensure that H is as close to the true concept as possible if it's deterministic, and if it is random, hopefully it does the best in terms of for any unseen instance. So we still need to formalize this bit. Okay. All right. So again, what is the goal of the learner? It sees training samples and the goal is to output this particular function. Now we don't allow one could consider all possible functions from the set of instances or the domain set to the label set. But as we will see later, it makes more sense to restrict your class of functions. You don't allow H to be any arbitrary function, but instead it comes from some subset of all possible functions, and this subset is called the hypothesis class. So the output of the learner is called a hypothesis, and the set of all possible outputs of the learner is called the hypothesis class. So again, when I say hypothesis class, if it's a strict subset of all possible functions, then it means that you know something about the problem already. That's some kind of an inherent assumption, right? But we'll see how the hypothesis class ultimately influences or determines how well the learner can perform. And at the same, so ideally we want the hypothesis class to be not too large and yet not too small. And we'll see what the interplay between these two is. Okay. So now suppose that I give you a training set, the learner outputs a particular function H. How do you decide whether this particular H is good or bad? Right? So of course we want to, we say that it should do well on a new instance. So one way of characterizing the performance of a particular hypothesis is to say, okay, suppose I give you a random function or a random instance X drawn according to the ground truth distribution, then how well does it perform? So in the case of classification, there's a kind of a natural way of determining this. What is the probability that the hypothesis is equal to the actual label? All right. So in other words, I mean, this is one way of characterizing it, or I can also say, what is the probability that you go wrong? If I see a completely random instance, then what is the probability that this hypothesis makes a mistake? All right. So in the case of classification, this is very natural. Again, recall that a classification problem is one where the label set is finite. So if the set of all possible outputs is finite, then it's a classification problem. If it's uncountably infinite, then we'll call it a regression problem. All right. So this particular quantity is what we will call the average risk, or sometimes the generalization error. Yeah. We will not discuss that particular framework of hypothesis testing, but we'll see what happens. In fact, we will see hypothesis testing in some way, but for now, let's look at this particular problem. So I will denote the risk or the generalization error for a particular hypothesis by R of H. But one thing that I want you to keep in mind is that this R of H depends on the ground truth distribution Pxy. Right? That's something that you should always have at the back of your mind. So basically, this probability is with respect to Pxy. Okay. So this is true for classification. Right? When the label set is finite and you want to predict the label correctly. Now, in the case where the label set is not finite, if it's infinite, as in the case of regression, for example, you want to predict the temperature tomorrow. Right? That's a classic regression problem. Now, you can't really predict the temperature with 100% accuracy. Right? All you can say is that your predicted, all you can demand for is that the predicted output is close to what actually happens. Right? So in that case, we need some measure of similarity, and that measure of similarity will be what I call a loss function. So we'll define a loss function L from y cross y to the set of all non-negative reals. In general, it could be set of all reals also. And the goal, the average risk in general is going to be defined as the expected value of the loss function, the expected value of the loss between the predicted output over a random sample and the actual label. Okay. Now, can you see why this is a special case of this particular formulation? What would be the loss function for the classification problem in this particular framework? Correct. So basically, the loss function would be the 0, 1 loss, which takes the value 0 if you make a correct prediction and 1 if you make an incorrect prediction. So the 0, 1 loss, which is relevant to classification, is where L of y1, y2 is 0 if y1 equal to y2 and 1 if y1 is not equal to y2. And I will represent this using the indicator function, or which is indicator y1 not equal to y2. Sometimes I will use the following notation: indicator y1 of y2. The reason why I'm using this particular notation, or this is a particular form of the following notation, indicator some set A of y. So this function takes the value 1 if y belongs to this set A and 0 if it does not belong to this particular set A. So in fact, this should be y1 complement y2. So it takes the value 1 if y2 is not equal to y1, and it's equal to 0 if y2 is equal to y1. Okay, so that's one particular loss, but you can define a number of other losses. Some commonly used loss functions are the squared error loss, so L of y1, y2 is equal to y1 minus y2 the whole squared. And another example is the absolute error loss. Which is just the absolute value of y1 minus y2. Now, of course, here in these two cases, I'm assuming that y1 and y2 are real numbers. But more generally, if you have an arbitrary label set, then you can define your own notion of similarity. And the generalization error is always the expected value of this dissimilarity, so to speak. Okay, so the way we define this loss function is that ideally we want the loss function to be smooth. So it's some measure such that larger L means bad and smaller L means good. Okay, any questions so far? Okay, but one thing to always keep in mind is that this generalization error is measured with respect to an independent sample, an independent random sample so it's statistically independent of your entire training set. Okay, that's the framework that we will operate in. Okay, and when you say that a particular algorithm generalizes well, it means that it achieves a small generalization error. All right. Okay. So now suppose that you come up with an algorithm, right? So again, let's go back to the pipeline of designing or what the learner is expected to do. The learner sees a bunch of training samples and then it designs an algorithm and outputs some hedge. The performance of this hedge depends on an independent random sample. It's the generalization error. Okay. Now, the overall generalization error, in fact, if you think about it, has two sources of randomness. One source of randomness is because you're evaluating this algorithm or evaluating the performance over a random x comma y. But there's also another source of randomness, and that comes from hedge. Because if you think about it, how are you generating the hedge? How is the learner getting hedge? Correct, it's taken from the hypothesis class, but how you choose from the hypothesis class depends on the training set, and that itself is random. So if your training set is kind of nice, then you may choose a good hypothesis hedge, but it may so happen that you design the best possible learning technique, but you happen to see a bunch of bad samples, and you end up with a bad hedge. So things can always go bad with a positive probability. Okay? So the thing to keep in mind is that there are two sources of randomness. right? So H is a random function in general, and because it depends on the training set x1 y1 up to xn yn, right? Because you choose H based on some rule. The second is, of course, random x comma y, which is independent of the training set. Okay, so henceforth I'll use the following notation. So S will essentially denote the training set. So it is x1 y1 up to xn yn. I'm sorry, you have the general definition of R of H.
Yes.
This expectation is, so this is for a, remember that R is for a given H. So this expectation is over this x comma y. It is sampled according to Pxy, which is the ground truth distribution, but x comma y here is independent of the training set. What do you mean expectation over all the samples? This is expectation is with respect to a new random sample out of the train, which is statistically independent of the training set. What do you mean all the samples? You mean over x1, y1, x2, y2? No.
Only once.
So it's a new sample. So that's the point that I'm coming to, which is that generalization error R of H is a random variable in itself, right? Because H is a random quantity that depends on the training set, correct? In general. Now, if you fix a particular H, if your H didn't come out of a learning procedure, so to speak, or you used a dumb learning procedure where you always output the same function, then of course there's no randomness left anymore. But in general, this R of H is a random quantity that will depend on the training set. H. If H is fixed, then there's no more randomness left.
But again, we are performing this expectation.
The expectation is with respect to only a new x comma y.
But that new x comma y is random.
X comma y is random, yes.
So then we can do any x comma y, then that can also.
It is, right? That's why I'm taking the expectation, right? What is this? This is just equal to assuming that x comma y is, let's say, or if you want x comma y to be discrete, then it is exactly this particular function, which is summation over all x comma y, pxy of x comma y, L of h of x comma y. It is this function, right? This is the definition of the generalization error. You're summing over all x comma y because it's an expectation, right? It's a weighted average, weighted by the probability mass function. The 0,1 loss will just end up being, so what is the 0,1 loss equal to? So again, there are two things, right? There is the loss function L, and there is the generalization error, which is the expectation of the loss function. So In case of the 0, 1 loss, what is R of H equal to? I'm saying that it is expectation of indicator function H of X not equal to Y, correct? Which is what? It is just summation over all possible X comma Y, Pxy of X comma Y, indicator H of X not equal to Y, right? So in other words, you're only summing over those X comma Y. I mean, this takes the value 1 if H of X is not equal to Y and 0 otherwise. So this is just summation over all xy such that H of X is not equal to Y, Pxy of X comma Y. What is this? It's just the probability that H of X is not equal to Y.
But we are summing over all X.
This summation is effectively only over those X comma Y such that H of X is not equal to Y.
Previously, when we denoted only the probability, not the summation.
What do you mean? It's an expectation, right? An expectation is a summation. Right? Yeah.
But it is only the probability of H of X.
Correct, but that's by definition equal to this.
It takes all
right?
the mass and
this is by definition equal to probability H of X not equal to Y, right? Where X and Y are new random variables. Another way is this is notationally the same as the probability of getting an X comma Y such that H of X is not equal to Y.
This collection of all X comma Y.
Correct. So, yeah, it is the probability of observing an X comma Y such that H of X is not equal to Y. Right? Okay. Any other questions? Okay.
So that exponentially comes for the 0 1 loss.
Which one? The probability that H of X is not equal to Y. It's very particular to the 0 1 loss. Right. So I was trying to make the point that the generalization error depends on, I mean, it's a function of H. So in general, this R of H is going to be a random variable, right? So it depends on your training set S in general. Correct? So, okay. So now the question is, how should you choose H? And okay, once you fixed a particular H, how do you choose a little H from this hypothesis test? Correct? So let's see what happens if your hypothesis test H is extremely large. So let's consider a scenario. Let's maybe go back to let's take any prototypical problem. Maybe let's go back to the problem of determining whether an apple is sweet or not. What are the measurements? So you get these apples. What does your training set consist of? It consists of a bunch of apples, and you make measurements, which is maybe the size of each apple, maybe the shape, and perhaps the weight of each apple. Okay, so you get a bunch of measurements, and you of course taste those apples to see whether they're good or bad. So each xi in this case is the measurements that you made, so it's a vector, and yi is the label which tells whether it is sweet or not. Now suppose that you're allowed to choose any function. So now you're given this, and the goal is to choose a particular H. Right? And one particular choice of H, if there are no restrictions whatsoever, one bad choice of H is to declare that if I get the same measurements as what I have seen before for a good apple, then I declare it to be good. If it is anything else, I'll declare it to be bad. Okay. So in other words, I'm looking at a problem of binary classification. There are only two classes. So from the training set, I'll separate them into two subsets, the set of all good measurements, the set of all bad measurements. Okay. So let me split training set into two subsets. Let me call x1 to be set of all x which belongs to the training set, such that the corresponding yi is equal to 1, and maybe x2 is the set of all xi such that yi is equal to 2. Okay, so one choice of H. So if I see a new observation x, then you declare H of x to be equal to 1 if x lies in x1, and equal to 2 if x does not lie in x1. Equivalently, I could define it the other way around. So declare that it's equal to 2 if x is in x2 and 1 otherwise. So how well does this perform on the training set? Perfectly, right? It makes zero error. But do you think this is going to be a good choice? In practice, it's going to be bad because you haven't really accounted for anything. Correct? So this is an example of an algorithm that does not generalize well. It achieves zero training error, but the generalization error will probably be pretty large. So then what do we do now? The problem that we have over here is that the class of functions h that we have is too rich, and choosing a very rich class of functions leads to this phenomena of overfitting. You do extremely well on the training set, but do terribly on a new sample. Okay, so how do you choose h? That's not very simple. It of course depends on what you know about the problem beforehand. Right. So in some sense, you want h to be not too large, and at the same time you can't have h to be just one or two functions, because then you may again incur a very high generalization error because your function class is not rich enough, right? So now let's suppose that we've fixed a particular hypothesis class h. From this hypothesis class, how do we select an appropriate function h? What should the learner do? So the learner is given this hypothesis class h, is given the training set S. Again, remember that the end goal of the learner is to output a h for which the risk is small. Right? We want expectation of L of h of x comma y to be as small as possible. And this is over a new x, which is not present in the training set. Correct? That's one thing to keep in mind. The performance is over something you have not seen. What is the most natural thing to do? So the goal, of course, is to output a h for which this particular quantity is small, right? But this is over a new sample, an independent sample, which is independent of, statistically independent of the training set. So how do you choose a h? You could, but then you don't know pxy, right? That's the fundamental difficulty. Correct. So the natural thing is to try to approximate this expectation with the empirical average, right? So use the empirical average as a proxy for the expectation. Let's look at 1 over n, I equal to 1 to n, L of h of xi comma yi. Now this depends on the training set. So this, I will denote this by r subscript s of h. All right. So this is an empirical estimate of the risk, and this is what we'll call the empirical risk.
Solution not over.
I'm sorry?
No, when we take the h is not,
Correct.
this can be 0, that doesn't imply the proper.
Correct.
We solve.
So we'll just fix a particular h which is not too large. Okay. I mean, we'll see. I mean, we'll explore more of it as we go along. So there'll be two things. One is the size of h itself, and the other is how well h approximates the ground truth. The class h approximates the ground truth. Correct.
It so happens that if a capital H is also not too large, then also it belongs to the family.
That can potentially happen. That can potentially happen. But as we'll see, if capital H, the hypothesis class, is not too large, in fact, we start out with a very basic case where h is finite. We see that if it is finite, then if you have a large enough training set, then you will not run into problems at all. Okay, and then we'll explore what happens when h is infinite. Of course, in practice, how you choose h is really that is an art in itself. Correct. So you want to choose a h which is not too large but is still rich enough, and that is what has taken so long to come up with good algorithms that do well on a large variety of machine learning tasks. So the way this will go forward is that given a particular h, we'll try to quantify the performance of any learning algorithm on this h. So h is in some sense decided beforehand. Okay. All right. So for a given training set, this is how I define the empirical risk. And one way of choosing a h is the so-called empirical risk minimization principle. Or ERM for short, which is, so HS is going to be the argmin H in H of the empirical risk. Again, note that this is one particular way of this is one particular learning algorithm. There are other variants of this, right? So right now what we've assumed is that you fix a particular H. There are other techniques, for example, what is called structural risk minimization, wherein you look at different classes of H. And for each class, you, in addition to, you don't just minimize the empirical risk, but rather some combination of the empirical risk and some measure of complexity of the function H. So maybe the number of parameters that is involved, free parameters involved that is in H. So you penalize taking a more complex function, something that has too many parameters in it, but at the same time, you also want to have a small risk. So if time permits, we'll look at structural risk minimization as well. But for most of this course, we will assume that we're operating under the empirical risk minimization principle. So this is what the learner will do. Given a training set, given a particular H, you choose H so as to minimize this empirical risk. How you minimize it is totally up to you. So there's another challenge, which is performing this optimization problem. The computational complexity may be fairly high, but we'll assume that you can do it somehow. So assuming that you're able to do this, what is the performance that you can get? Okay, so this is one particular framework, and again I'm denoting this S as a subscript to indicate that this is a function of the training set, right? So now the question is, what kind of guarantees can we give? As I said, we want to minimize the generalization error, but the generalization error is in itself a random variable. So how do we, so generalization error captures the performance of a particular H, but it doesn't really characterize the performance of the learning algorithm itself. It tells you how well a particular H performs, but it doesn't tell you, for example, if empirical risk minimization is good or not. So in order to characterize that, we will use the so-called PAC framework, or the probably approximately correct framework. So what we want is that the probability, now this probability is over the training set, that the loss or the risk achieved by this HS is too large. I'll make it a little more precise. The probability that this is greater than or equal to, for now let me just keep it at epsilon, should be less than or equal to some particular delta. Right? So this is sometimes called the error. Let's suppose that I define it in this particular way. Right? So now there's no randomness involved anymore. Correct. Correct.
Empirical and RS.
Correct.
That RS of that's not the test figure.
So this is not, so R of HS is not the empirical risk. It is the generalization error.
That test is point. training set.
Which the R is not evaluated with, so this R is not evaluated with respect to the training set. This R is evaluated with respect to a new independent sample, but HS depends on the training set. Correct? So yeah, so these are these subtle notions that we'll have to get used to, right? And that's why I'm using the subscript S to differentiate between each of these.
That was that RS of it, right? That is no longer related to the training set.
Which RS of H depends on the training set.
Okay, that is calculated.
Right? Yes. Whenever something is subscript S, it means that it depends on the training set S.
Okay.
So here it depends on the training set because it's the empirical average calculated with respect to the training set.
And then depending upon the alphabet H, this could lead to arithmetic also.
Correct. Potentially, yes, that could happen. Definitely. So again, if we go back to the sort of toy example that I gave earlier of choosing an apple or predicting whether an apple is good or bad, note that if I use the empirical risk minimization principle, then this particular algorithm actually achieves zero empirical risk. But there are multiple functions H that achieve zero risk. The question is now, how do you choose the one, which one do you choose? And that is effectively what all of this boils down to. Which in general you use something like gradient descent or stochastic gradient descent, right? That's how you do it in practice.
Apart from these,
I mean, any optimization algorithm in principle will work, right?
apart from iterative methods, post-functional.
Except in very specialized cases, there is no. I mean, even if when it is non-convex, even convex, you don't have a closed form solution, right? It's still some kind of an iterative algorithm, like gradient descent or Newton's method.
All the small h with an alphabet is just because by parameter.
Which one?
All the hypotheses
Correct.
like are on the same framework but with different parameters.
What do you mean different parameters?
If
Whatever. So all of that is collected into this capital H.
that capital H could contain different styles of hypotheses.
Correct.
When we use like
So, for example, capital H could be the set of all neural networks of with certain parameters. For example, certain number of layers. Maybe, yeah. It depends on the class over which you're trying to find this. It could be the class of all neural networks of, let's say, depth at most 10, where each layer has at most, let's say, 100 neurons. That's one potential choice of H, right? But again, for us, everything is abstract. Okay? So the goal will be in some way to characterize the complexity of H. That's what we will be heading towards, without worrying about the specific structure. So what really determines whether H generalizes well or not? What really determines whether H overfits or not? Okay, yeah, so coming back to this subscript S, one thing to keep in mind is that you have these different quantities. So let's just get used to it. So remember that for a given H, you have RS of H, which is the empirical risk. Empirical risk with respect to the training set. Achieved by H. you have R of HS, which is the generalization error, achieved by, maybe let me do it step by step. I have R as R of H, which is the generalization error achieved by H. So this is over a new sample. I have HS, which is the minimizer of the empirical risk. It's the minimizer of the empirical risk, which is RS of H. Correct. I have RS of HS, which is the empirical risk achieved by the minimizer of this, which is in fact the minimum empirical risk. With respect to this training set. And there is R of HS, which is the generalization error achieved by HS. The point to be kept in mind is that HS achieves minimum empirical risk, but is not guaranteed to achieve the minimum generalization error. Right? So that's a key distinction. The H that minimizes the generalization error could be different from the H that minimizes the empirical risk. If somehow the empirical risk were equal to the generalization error, then yes, both of them would be the same. But in general, that is not going to happen.
Empirical risk is in
Which one? Not necessary.
depends on
Depends on H. Yes. Any questions so far? Great. So again, let's now get into this definition of being probably approximately correct. So probably is because there's always some amount of randomness.
Sample.
Correct.
You need a set of new data points.
Okay. So again, it's not a set of new data points, right?
They are independent of training set.
That's how you evaluate or approximate the generalization error in practice. But actually, what you want to achieve is minimum over a new random sample. Right? If somehow there is, let's say, an oracle which can generate a new sample for you, then on average you want to do well.
It will generate multiple samples of the scale.
Whatever. If you see just one random sample, or yeah, of course everything is so. If you take it from the empirical view, then for a new set of samples you want to achieve small average error. But again, we've assumed a probabilistic version of the ground truth. So if I get something from the ground truth, then it should do well. And in fact, that's, yeah. So let me just make a comment since I'm already speaking about that. So So that's the whole purpose of, so if I go back to the sort of approach that is used in practice, you have your data, you split it into training, validation data, and test data. Right? The whole point of having this test data, which is separate and typically picked according to the same distribution as the training data, is so that this test data approximates the generalization error. Right? Because the H that you have chosen from the training process is independent of this particular test data. The empirical average or the empirical loss that you compute over the test data, you consider this as an approximation of the generalization error that it can achieve. And that is why it is extremely important that you never take any decisions for the training algorithm based on what happens when you get the test data. The test data is always to be seen at the very end after you have optimized and done everything else. Once you evaluate the performance over the test data, you should not go back. Because otherwise, the results that you get for the test data is completely meaningless, because it is not an approximation of the generalization error anymore. Right? Okay. So now the goal is to come up with a training algorithm such as the empirical risk minimization algorithm, which performs well. And how does it, and the performance of a training algorithm is measured using this probably approximately correct principle. So what you want is that the empirical risk or the generalization error should not be too large, so it should be approximately correct. But you can't say that you will be approximately correct all the time, because your training set is random. So all you can say is that you are probably approximately correct. This was formulated by Valiant back in, I think, 84. I'm sorry, not Valiant. Wazirani. Back in 1984. And this is really the principle that is used in most machine learning algorithms today. Okay, so I've defined things in this particular way, but do you see that there's a problem with this definition? Of course, it depends on epsilon and delta. That's fine. Yeah, that's okay. I mean, how you compute it is not really the issue over here, but do you think this is a reasonable thing to expect? Is this a good measure of performance of a training algorithm? RS of HS, that's okay. That's not so. RS of HS is what you use. I mean, that's one way, right? So a particular training algorithm. So this is for one particular training algorithm, right? Which is the empirical risk minimization. But in general, I could have any arbitrary learning algorithm, not necessarily using empirical risk minimization. It could be structural risk minimization. It could be something totally different, right?
Over the training.
This is not calculated with respect to the training. Which correct. I mean, the probability is over S, because whatever algorithm you use, the output of the learning algorithm, which is the function H, depends on S. The that's only randomness that is left, right? So Okay, so let me not use HS, but let me just have,
It is the specific property for the corresponding prime.
okay, so let me go at it step by step. So what is the framework? You observe, you get the training set S, right? From this, using this particular training set, you output H, let me have superscript S, just to emphasize that this H is going to depend on the training set. It of course depends on the hypothesis class as well, right? And then using this, so this is what you're going to use for testing. It achieves some test error or some generalization error, R of H of S, correct? So this is some quantity, it's some number that depends on this particular H,
That in turn effectively depends upon the pattern.
correct? Because of the way you have chosen H,
It's based on S.
that is dependent on S. It may be dependent on S, it may not be dependent on S. Maybe you just always output a particular function H. That's also a possibility. But this S is to indicate that in some way, if it is allowed to depend on anything, it's allowed to depend only on S. So now, assuming that this is true, do you think this is a good measure of the performance of any training algorithm?
It relies on that as a representative.
That's okay. I mean, that's why I'm taking the probability with respect to S.
How good it is performed with respect to remaining.
Okay, that's fine. Of course, that of course depends. So in other words, it does tell you how good your algorithm is, right? Because if your algorithm were dumb, then you would perform badly relative to the rest of the hypothesis class. And if it were good, then you would perform much better than the other H in the hypothesis. That's okay. That's still okay, right? So I'm saying that this is any algorithm. I'm not restricting myself to empirical risk minimization or anything else. So right now what I'm trying to do is, in some sense, compare different training algorithms. Is there something else that is missing from this mix? Can I always achieve this? Is there always an algorithm that achieves this? What if there is no minimum or what? So here I'm not. What do you mean RS of H is not minimized? That's okay. Again, I'm not worried about the complexity of finding HS, right? I'm assuming you have all the computational resources in the world. Delt, okay. And why do you think that's not possible?
I think when you fix that sandwich,
Okay.
the quantity on the left hand side is kind
Okay. Fine.
of, you can't just like arbitrarily.
Potentially, I mean, so S in some sense depends on the number of samples, right? Maybe I can just increase the number of samples to keep shrinking it. There's another important thing that is not included in this yet. That's okay, we fix a particular loss function.
Of the loss of this event.
Okay,
All algorithms.
Okay, that's a good point. So what do you think I should change in here?
It's like the minimum possible gain.
Correct, the minimum possible generalization, right? So so it's maybe not possible to achieve arbitrarily small epsilon because it may depend on the loss function L itself, but more importantly also depends on the hypothesis class, right? If I chose a bad hypothesis class, then even the best learning algorithm is not going to do well, right? So whenever I want to evaluate the performance of a learning algorithm, it can only be measured with respect to the best hypothesis in this particular hypothesis class. It can't achieve a smaller generalization error than the smallest one achieved by this entire hypothesis class itself. So one way to fix that is to say min over h r of h. So relative to the best performer in this hypothesis class, how worse off is my learning algorithm output? Right?
Where we get
You mean evaluating this from the samples? You can't, right? That's true. But then it's sort of like the way we treat the ground truth. There is some underlying ground truth which we don't know what it is. But the beauty of it is that you can still say something about it without knowing what it is. Which not really. So again, in practice you don't look at this, right? In practice you never do this. The point of developing this theory is that in practice you don't have to worry about this. What we will show is that you can get this. So note that this is the best that you can possibly ever hope for, right? You can't do any better than this. That's something you can easily convince yourself. The point is that you can get something close to this, and that is what you do in practice. To make it more meaningful, exactly. Because otherwise, now this is something that can be achieved, right? Because the smallest r of h that I can ever achieve is this particular quantity. So what this statement is saying is that I'm not doing, so suppose there were a genie which knew what the best h was, then that would choose this particular, then that would achieve a generalization error equal to this, correct? This is a genie who doesn't see the training sample but actually knows the hypothesis class, knows the underlying distribution, right? That would achieve this risk. What you're saying is that an algorithm is good if it achieves within an epsilon of what the genie can achieve.
Belongs to algorithm.
H belongs to the hypothesis class, yes.
is greater than or equal.
Which epsilon?
Epsilon is greater than or.
Epsilon is greater than or equal to 0. That's
But how we calculate minimum
which one?
or
Again, we won't be worried about how you calculate it. In fact, it's not possible to calculate this. What does minimum of r of h depend on?
OX?
It depends on the ground truth pxy, right? You don't know that.
Then what is the meaning of defining the bound of R?
It is, so that's what we are comparing ourselves to a genie who knows the ground truth, correct? So it's a very strong requirement, right? It's an extremely strong requirement, saying that if there is some genie who knows exactly what the ground truth is, and this genie does the best thing possible me with my algorithm, with my limited training information, I still want to do something which is almost as good as the genie.
When we don't, we expect.
That's the point. That's the point, right? I mean, it's not possible always. There are certain restrictions, but as we see, these are very, very mild restrictions. Even with extremely mild restrictions, you can do almost as well as the genie. Right? Of course, I'm throwing a lot of things under the rug, such as how do you solve this optimization problem and so on. Not this optimization problem, but rather, let's say, empirical risk minimization. And that's really, I mean, the choice of using something like stochastic gradient descent to solve empirical risk minimization, it comes out of these principles. It's not just a heuristic. It is grounded on these probabilistic results, which say that yes, it in fact does well in general, in some of the most general scenarios.
S is a classic written by an algorithm
Correct.
based on the hypothesis.
Correct. This H superscript S is a classifier output by a learning algorithm. Any learning algorithm.
And is also
ERM is one learning algorithm. Right? So we'll say that a particular hypothesis class H is PAC learnable in fact we'll sort of make this even stronger in some sense. So we'll say that H is PAC learnable if the following happens. If for every epsilon greater than 0, delta greater than 0, it's possible to, there is some number m, which of course depends on the hypothesis class. It depends on epsilon and delta. Right? The key point is what I have not included in this, which is such that for every ground truth distribution, there is some algorithm which uses these many samples, at most these many samples, and still achieves this particular quantity. I'm sorry, I should touch that. Is a So in other words, for every, that is the number of samples that you need in order to do a reasonably good job, depends only on epsilon and delta and is completely independent of the ground truth. Your ground truth could be extremely skewed, doesn't matter. There exists a learning algorithm that uses only these many samples. If you have at least these many samples, then you're guaranteed to do well.
Well, it's greater than R.
Epsilon is greater than 0. That's it.
Is R equal to minimum of R?
That's okay. So I won't set epsilon equal to 0. That's in general too strong a requirement. All I'm saying there is that I can get arbitrarily close to this minimum. Not necessarily equal.
MH of Z.
I'm sorry?
MH.
Yeah, MH depends on the hypothesis class. It's an integer, it's some positive integer, which is allowed to depend on the hypothesis class. It's allowed to depend on epsilon and delta, but independent of the ground truth. So no matter what the ground truth is, you should still do it. N is the cardinality of S. Maybe let me put that explicitly. Question? Okay. So in fact, there are some slightly different definitions depending on the reference that you use. Some of them, in addition, also demand that this particular m subscript h, it's not just any arbitrary integer. You also want it to be a polynomial in 1 over epsilon, 1 over delta, and the size of h. So for example, you don't allow m to grow exponentially in the size. But in fact, we'll see that that is not really a terrible requirement, because in general, h could even be infinite. And that's really the more interesting scenario. Any questions? Okay, so in the next class, we'll go over a very simple scenario wherein you just want to do binary classification, and we have a finite h, and we'll also assume that the ground truth belongs to this hypothesis class. Right? So in other words, you're trying to find a h from the concept class itself. You know what the concept class is, and your goal is to find the classifier from this particular concept class. And we'll make use of some of the results that we've seen, essentially just the Chernoff bound and union bound, nothing else. Using just those two tools, we'd see that in fact any finite, at least for this particular problem, a finite hypothesis class is always pack learnable. That can be very easily generalized without much difficulty, that even for, say, general classification or even regression, as long as you have a finite hypothesis class, that hypothesis class is pack learnable. Okay, so let's stop here. Any questions?